Welcome to the Roundtable on Photonics Foundries. My name is Daniel Renner from Freedom Photonics, and I will be chairing this panel discussion. The structure of the discussion is as shown in this slide. We're right now at the introduction, and this will be followed by brief presentations from the 5 panelists. First, it will be Luke Augustin from Smart Photonics, then David Harami from SUNY AIM, then Thomas Hessler from Legion Tech, Gordon Harling will follow from CMC Microsystems, and then Gloria Heffler from Infinera. At the end of these 5 presentations, we will open up the forum for discussion. And here, of course, we welcome the participation of the full audience. If you have any questions or comments, please send those either through the chat line. I will be monitoring what questions come through there, or you can open up your microphone as well and ask directly. The participation from everyone is highly encouraged. Obviously, this is a very relevant and important topic, and we would like to have a discussion that encompasses as wide a range of opinions as possible. So the discussion should take something around 45 minutes or so, and we're aiming at finishing by 11:45 Eastern Daylight Savings Time. I posed a number of questions to the panelists to focus their thoughts on. These are not the only aspects, obviously, that we will be talking about or they can talk about. The discussion is open, and any relevant topic to Photonic Foundries is welcome. But the questions that we would like to focus on are, number one, as indicated there, what aspects of electronic foundries can be replicated in Photonic Foundries. Obviously, electronic foundries have a far longer history compared to Photonic Foundries, and obviously there is a lot to learn there on what to do, and that would be question number one, and what not to do. And that would be question number two, either because electronic foundries maybe made mistakes in what they were doing and then they corrected, so we should not replicate that mistake, or just because obviously primarily silicon electronic foundries are of quite a bit of a different nature to to photonic foundries, whether they are silicon or 3.5 or any other type, and these differences need to be recognized. In using the term photonic foundry here, we use it in as wide a sense as possible. So we're including silicon photonic foundries, CMOS foundries that are primarily electronic, but are incorporating some photonic components, 3.5, indium phosphide, gallium arsenide, photonic foundries. We're taking the term photonic foundries as wide as possible. The third question is, what are the unique aspects of photonic foundries that are key to their success? What are the things that we need to do to make sure that photonic foundries are successful, which they should be and they will be? And the last question is, how can the photonic industry support the evolution of photonic foundries and the inclusion of photonic components into electronic foundries? So what is it that we can do to help here and make sure that we get a strong photonic foundry support in the industry? And obviously, as I mentioned earlier, any other relevant topic to photonic foundries is welcome. There's no need to limit to these questions. Any other question or topic is fine as well. So having said this, I will let the first panelist to start. And that is Luke Augustine from Smart Photonics. So Luke, please go ahead.
Yeah, thank you, Daniel, for the introduction. And thank you all participants for joining this panel discussion. And in the next 5 minutes or so, I want to give you a bit of a flavor on Smart Photonics' view on photonics foundries and what we can learn from, well, actually, as Daniel just introduced. So my name is Luc Augustin. I'm CTO of Smart Photonics. I have about 20 years experience in photonics. I did my PhD in electrical engineering in Eindhoven University on photonic integration. After stepping to the solar cell company, I got back into photonic integration and was co-founder of Smart Photonics in 2012. So that brings me to well, introducing Smart Photonics. So Daniel, if you can go to the next slide, please. And so Smart Photonics, in summary, is an open foundry. So we offer manufacturing services for indium phosphide-based photonics. So we have our manufacturing processes in place that we use to help our customers make their circuits. So what we are unique in is that we have process know-how, technical capabilities to actually make these indium phosphide photonics, and we do that in an open foundry way. So we do not have our own products, but we solely work for our customers. Well, next to that, well, we work on indium phosphide. So indium phosphide offers the capability to really monolithically integrate active and passive components. So SOAs, lasers, light sources, as well as high-speed modulators and passive circuitry. So in fact, it offers a full-scale monolithic integration. What we do have is a standardized and a validated PDK's process design kit, in which a number of building blocks, all the elements like a laser, like an amplifier, like a modulator, they are in there. So a customer does not need to develop them from scratch, but can use them to design their circuit. And that can be applied to a broad range of use cases. So not only in telecom, but also in optical sensing markets and things like LiDAR and other upcoming technologies. To do all that, we have our own production clean room. It's about well, over 1,000 square meter production, where we do epitaxial growth as well as the whole semiconductor processing, the backend and testing. And next to that, we have access to a separate R&D facility at Eindhoven University, but we still do use to develop our next generation components. So that is Smart Photonics in a nutshell. If you can go to the next slide, please. So our heritage is actually built on, well, actually a long history here in Eindhoven in the Netherlands region, where it dated back in the 80s and 90s in Philips, where they were first making lasers. So really making lasers for telecom operation. That was acquired by JDS Uniphase. And so there was really a steady commercial industrial operation to make lasers. Next to that, there's Eindhoven University. They did a lot of work on integration, on monolithic integration on indium phosphide. So design and define new aspects of indium phosphide, make new building blocks available, and with integration in mind to make full-scale integrated circuits. And actually those two lines of expertise merged into Smart Photonics in 2012, when we actually spun off from Philips. Philips decided to stop the 3.5 activities, and together with university, we founded Smart Photonics. And as of 2012, we're operational, where in 2013, we had the first commercial multi-project wafer to show this capability of this process design kit, where people can design their circuits and at a cost-effective way. And after that, well, we moved to our facility where we are now with our new clean room, and we are currently investing heavily in ramping up the capacity. But that is Smart Photonics, the heritage. So there's both from the academic world, from the research world, from the integration has been developed here, as well as the knowledge of the industrial scale application of indium phosphide lasers. So if you can go to the next slide, please. So if we look at our business model, it's really almost copied from what we learned from electronics, where really we want to be a successful foundry. In order to have a successful foundry operation, you need to standardize processes, and to that other people, even small customers, can leverage from the existing volume, and with that we can also utilize our capacity to the most efficient way. I think that is something that is done in electronics. That's for sure something that we need to work on to get that. Next to that, an extensive PDK, including compact models to allow higher level design. So you need to have well-described devices in the PDK that people can use to design their circuits, and that they do not need to design on a quantum level or a doping level of their circuit, but they can design, well, I need a laser with this output power, or I need a laser with this wavelength, I need a modulator with this V pi and RF properties. So that's all in our PDK. And that is the way, well, it is done in electronics, and that's what we want to adapt. And the next thing is the methodology for wafer acceptance, so that we allow high throughput on wafer electrical testing. There's PCMs, so process control modules, test methods on wafer, extraction of parameters for the compact models, and of course, importantly, design rule checking, automated design rule checks. So that is all kind of standard in electronics, and this is adopted into photonics, and we are ramping this up to more mature ways of dealing with this, and that is a requirement to get this model working. And that is really this standardization of the processes, but also the standardization of the PDK that can really lead to a cost down, and that can enable scaling to volume. And next to that, so that is more the foundry side of things. On the other side, the ecosystem that is present in electronics, where there's IP blocks, where there's companies that solely live from designing IP and selling it to others, license building blocks. I think that's something that we can adopt even more, and the infrastructure is there, and this ecosystem has to grow, and that can give another boost to photonic integration. Can you go to the next slide, please? I think a few things we should do differently in our view, and that is in electronics. There's a few big names for software design, and that actually prevents entry of smaller parties. So what we see in photonics, there's really a large choice of software, and cheaper and very sophisticated software. But the good thing is, if you standardize on PDK level, if you standardize on modeling, if you standardize on design rules, you can allow multiple software vendors or even homegrown software to work with these, and that enables other companies, even smaller companies, to work with photonic integration. I think that's something that we have to adopt. And in the end, we see, well, that any software can use there. And the other thing is really we have to grow with the market demand. And people are sometimes laughing at the wafer size that we still work with in indium phosphide, but that can be very cost effective. And actually that fits nicely with the demand now. And we can grow with more wafers and bigger wafers, and with that we can easily cope with the demand. And we can actually look at the electronic tool developments, and we can build on the infrastructure that is there. I think another point is really the geographical spread of the foundries. I think that's something that we have to work on as well, where electronics is really low. The high end, the high end electronics is located in one place in the world. I think with photonics, we have it spread over the world, and we think we should grow that in a similar way, that is more geographically spread. That can help the industry in multiple continents. So that brings me almost to the end of my presentation. I think the other thing is we have to look at the intimate integration with electronics to really choose the best of both worlds. So for photonics, we have several choices. For electronics, it's mainly silicon, and we have to find the sweet spot in which they integrate best. It's on one hand, so indium phosphide, we can do the lasers, but we can do more. On silicon photonics, you can do very high volume, very nice passive circuitry with limited additional functionality. And I think we have to find the sweet spot between the two. And once if you're indium phosphide, you can do a lot. Once you enter the silicon, then don't try to go back and forward to indium phosphide, but try to make more functionality on indium phosphide and go to silicon ones, and then go from die level to wafer level integration, and maybe even to see from photonics to electronics connection, because an optical connection is expensive and has very strict tolerances, but the electronics might be a better choice. So that will be, I think, the challenge for the next coming years on where to put the interface. So that brings me really to the end. So thank you for your attention.
Thank you very much, Luke. So the next presenter is David Harami.
Can you see my screen, full screen?
Yeah, we can. We can see all your slides, though. I think you might want to go to presentation mode.
Oh, I thought I was. Let me just see here. It was show the taskbar. Let's see. It was perfectly
that's
before.
good.
Pardon?
That's good.
It's full screen now? Huh. Okay.
We can see the next slide as well, but
oh no, I'm
pretty
trying to go
clear.
to full screen.
Yeah.
I'm not quite sure why it did what it did. It was, I guess I opened up something else and now it's changed my settings. Where's my ability to just have one screen? I don't know. Well, why don't
It
I
looks
just
very clear, though. We
Okay,
can see
all right.
well, so no worries.
Okay, all right. So first, let's all right. So first of all, my name's Dave Haramy. I'm the director of the EPDA test assembly and packaging and process development for the Research Foundation SUNY, and I'm also the chief operating officer for AM Photonics IEEE fellows. I've held many positions at IBM and Global Foundries, fairly experienced in the electronics industry. So first of all, as the COO of AM Photonics, I want to talk a little bit about that. It is one of 9 Department of Defense Manufacturing Innovation Institutes. These are really public-private partnerships, right, that focus on creating expertise. The mission for photonics really being to advance integrated photonic circuit manufacturing technology. That actually included both indium phosphide. Gloria will be talking about that, in silicon. I'm just going to focus on the silicon photonic side. Of course, meet commercial objectives, especially with current administration in the US. There's a large emphasis on building commercial and creating adaptive integrated photonic circuit workforce, a lot of educational workforce development. This shows sort of the 3 areas that have become sort of focus areas of the technology. One is we have a full photonic integrated circuit, silicon photonics platform. It has SOI, it has germanium photodiodes, it has various dopants, ridge etch, ability to make Mach-Zehnders and phase shifters, etc., active components. It has 2 nitride layers, and that gives an opportunity for quite a few waveguide design possibilities. In addition, we have an active interposer. We do electronic interposers, and we take this technology and actually flip it upside down, remove the backside, and let you have a lot of connectivity on top of the interposer and all the benefits of the silicon photonic technology. In Rochester, we have a 300 millimeter wafer and chip scale test assembly and packaging facility. So we basically have an end-to-end capability from the photonic integrated circuit design and MPW and custom build all the way through to the packaging. So the first question was what aspects can be replicated in a photonic foundry? I mean, basically, almost all the fundamental aspects of electronic foundries, right? We're really using the same kind of facilities, same kinds of tools. For photonics, you may want to steer those in a different direction, but basically it's the same infrastructure. We use process design kits, mostly electronic industry or electronic design automation. We really need electronic photonic design automation, but we're basically taking the same general methodology, and the same vendors. In large part, the larger ones are focused on delivering PDKs and design support. We have packaging facilities, much of the same type of equipment, except for photonics. Of course, it's really more of an art these days, and a lot of the cost is really in the packaging, and this really needs to be a lot more standardization to reduce the overall cost. And of course, we have the same kind of supply chain infrastructure. This kind of shows the facility here at the Albany at 100,000 square foot, 300 millimeter technology. This is just a snapshot of one of the fab areas. You can see the supply chain for transceivers. Transceivers are really the one application that is really ramped. And but the supply chain fundamentals are really much the same as they are in electronics. They're just simply some substitution of different types of specialties. And then packaging is really the same basic assembly infrastructure, but the photonics is another add-on that really makes it very different, makes it customizable. And this is really getting standards for coupling to these devices, attaching 2.5D devices. That's a big area of challenge. So what aspects are not supported? Well, first of all, the material requirements are very different. You're looking for absorbing material, scattering, film composition, refractive index, stress. None of these things are particularly important to somebody trying to make 14, 10, 7 nanometer sort of processes. They're trying to get very accurate control of small structures and thinner films, and photonics comes in and they really want thicker layers and different properties. So you could use the same tool set, but how they're used can be very different. The lithography priority is for smooth, large waveguide structures, compared again to trying to make a 7 nanometer device or something. Really, you're trying to make much larger structures, very accurate alignment, and have very smooth surfaces. So the whole challenge of OPC, mask, reticle enhancement techniques, it all has to be steered in a different direction than making a small SRAM cell, STI cell or something, gates. Very different. So the unique materials, in a CMOS fab, they are very sensitive to any kind of contamination that shifts or gives instability for any kind of MOS effect. The 3.5s, look at lithium niobate, barium titanate, all sorts of different materials. If you could integrate those together with electronics, now you have something that's really interesting. These materials are very difficult to get into a CMOS fab. So sometimes for integration, you may need unique materials, and that's difficult in a CMOS fab and electronic fab. Packaging, I mean, you're really focusing on optical coupling efficiency. Electronic packaging, especially for server class kind of devices, is bump density, chip stacking, really no fiber emphasis or coupling kind of emphasis, not these kinds of aspects where you're mostly focused on these builds. Today, many of those builds are unique. It's boutique. It's not everybody's different. It's not, there aren't a lot of standards that are really driving down cost in the industry. And photonic testing is very different. The whole test equipment is very different. How you connect to the photonic devices, there's significant data volume collected from these. So the testing regime is very different. So again, sort of the same overall structure, same kind of equipment, maybe same in design vendors, but very different kind of requirements. So what are the unique aspects that are key to their success? Well, we just mentioned fabrication, touched on process requirements, lithography, test. Reliability is another thing. It's largely speaking, people do interconnect reliability, maybe packaging level reliability, especially for the fiber connects, et cetera. It's very different than electronic. There just isn't the same level of learning on it. It's somewhat still emerging. Supply chain, there is a existing supply chain for transceivers. There are a lot of specialty applications. This is like electronics was in the 80s. There are just many emerging ways to use photonics. And that's a difficulty for the supply chain to support that. In large part, they don't support it very well. So it's difficult to get prototypes and really get new ideas into a development and then volume production. The roadmap, I mean, we're going to talk a little bit about the electronics roadmap, but it really needs photonics. It's very dependent on photonics. It's co-packaged electronics and photonics, optics on board. These things are going to drive high performance. And how you do that is only going to exist if it's sort of a synergistic kind of roadmap. And of course, EPDA really from the photonic integrated circuit, sorry for the typo there, through packaging. Education, workforce development, I mean, it's got to focus not just on new people coming into photonics, but really training incumbent workers and practical training in photonic design tools, which are very different than electronics. So there's really no design paradigm for this and how to teach this. And I think this is a electronic photonic integration. This is an important area. So how can the photonic industry support the evolution of photonic foundries? Well, I mean, fundamentally, it's volume ramps, right? If there's a lot of volume ramps and transceivers are doing that, then they're going to help standardize processes required to meet the demand. But there's some difficulties here. High volume photonic manufacturing, they're large. If you have a 7 nanometer fab and you've got these very large photonic chips, it really is compromising, leveraging that technology base. So there's a little bit of some conflicting requirements there, the size requirement. Heterogeneous integration can make some sense. Photonic industry should publish clearly articulated needs. There's a lot of road mapping activity, but that really has to drive development in sync with electronics, co-design. I think that's really important, and education workforce development. Any other thoughts? Well, I think we need to really emphasize that photonics is critical to high performance microelectronics. If you look out in these roadmaps, they're struggling to get much past 2030. Photonic integration can provide this I/O scaling. And I think what we're going to see downstream is more and more optics on board and more tight integration. And that goes back to all those comments about unique materials being integrated together with silicon photonics and large structures at the same time as you have small structures. This whole synergistic integration, I think, is going to be important. There are extreme advantages of 300 millimeter versus 200 millimeter. I mean, I know there was a little bit of a discussion about small wafer size, but you just get a lot more control if you're in the 300 millimeter fab, where you have all of this lithography, patterning, etching capability. If you're able to build 5 nanometer kind of structures, applying that to large structures to get very smooth interfaces and very reliable loss mechanisms, that's extremely valuable. So we need to take advantage of what's there, not just for feature size. Photonic packaging remains an art. It's until we get standards and really significantly agree on those standards, it's going to still be the higher part of the price equation for getting photonics things into prototypes and products. Many emerging applications are not getting attention from large foundries. Maybe transceivers are ramping, and maybe some of those applications, but the smaller emerging applications, they end up in more development, and then how they ramp to large foundries. That's not well supported. Having some kind of infrastructure where you have a matching, a mirrored technology in a large volume fab, and then a smaller development site, so you can support these things and more easily get them into large volume. I think that could benefit both types of fabs. And basically, we need more acceptance of different materials. I think that's sort of a net. So that's basically it for the presentation and some thoughts.
Thank you very much, David. The next speaker is Thomas Hessler.
Yes. Hello. Okay. Can you see the screen?
Yet.
Yep. Okay, let me quickly introduce Leitchentech. We are a European-based big provider.
Sorry, Thomas, but I don't think we can see your slides yet. For the share screen button at the bottom. There,
Yeah, I'm trying to it.
There, now it's coming. There, perfect.
Okay, so we are a Swiss-based company, provider for silicon nitride PICs. So we are a European company, let's say, headquartered in Switzerland and having co-workers in Spain and France. And our focus is thick silicon nitride with a high mode confinement, which is, we see it a little bit as a compromise between thin silicon nitride and the benefits of SOI silicon photonics. The whole process we developed is fully CMOS compatible, scalable, and has all the nice benefits of silicon nitride, as you probably know about. And the key applications we are targeting in is mainly LiDAR, quantum, and then smaller applications like space, sensing, and all these comp-based metrology applications which might come up in the mid-future. To myself, I joined Leitchentech a bit more than 2 years ago. And my background is more on the free space micro optics for optic transceiver market and also optical gas sensors for environmental and medical. And then also a little bit of high volume specialty MEMS foundry business. At Leitchentech, we developed a platform with different thicknesses, different process modules, all modular and independent, and also working on to get an extensive PDK. Yeah, with all what you need and what Luke already described quite nicely beforehand. So where are we positioned in the value chain? So I think it's very similar to Smart. We don't call ours open foundry, but we typically accept either the GDS from the customer or the circuitry layout, and then support the customer in the layout and design of the components. And delivery format is typically the known good die. Yeah, we recently announced a partnership with X-FAB to be able also to handle the high volumes for the markets up to come. So we implemented our process in their foundry ecosystem. To the questions, I don't want to repeat a lot, so most of that has already been touched. I think one thing we should not forget, what is different in electronics or in photonics is physics. I mean, there's no scaling in photonics, and that is always coming back to us in practice. I think that's an important point. Where do you see unique aspects of photonic foundries? I mean, of course, we say low loss, that's key, that you have your losses under control, but at the same time to offer high functionality and integration. And that leads to the fact that you probably have to handle different materials, since there's probably not one solution fits all. And then on the business side, I just feel a long breath and the ability to start small. So you have to pick it up from the ground. These killer apps and photonics, they might come, they might exist, but I would say, at least to our experience, the majority of the things there's hard work behind and a long time needed. How can the industry help? I mean, yeah, like always, interact as early as possible. That you can influence design from the circuitry all the way to the packaging, and then also we have the thing to be open to be flexible and to look into hybrid or heterogeneous integration to get to full working devices which are commercially viable. Thank you.
Thank you very much, Thomas. And the next speaker is Gordon Harling.
Great. I'm just waiting for the share screen to take over.
Yeah.
Maybe you can stop sharing there.
Yeah, if I find it.
There,
That's
good.
better.
Okay.
There we go. Now, CMC is actually a slightly different organization. We don't actually have a physical foundry or anything else. What we do is we amalgamate. So these numbers only go back to 2018. We're actually over 100 designs a year right now, and we aggregate into a variety of different foundries. You can see a bunch of the logos there on the bottom left. Very proud of that. And we do a lot of training. So a number of people have mentioned HQP. So we have a format called Basecamp where students take 3 weeks of intensive tutorials and workshops and lectures. And then we give them tools in the cloud for 3 months. And we've served students in Europe and Australia, in the US. It's not just Canadian students, and both industry and academics. And then after the 3 months of tool time, they submit a design, we fabricate it, and they test it. So in the case of the University of British Columbia, who hosts this, they actually give 3 credits for following the coursework and 3 credits for providing a test report. So it's a really, really useful scenario for folks wanting to learn how to design and build and test silicon photonics. So we're very proud of that. And that is how we've come up with 950 designs in the last 12 years. We also support a variety of foundries. So AMF, we're actually the worldwide aggregator for AMF in Singapore, the Advanced Micro Foundry. And they take Chinese and Japanese companies direct, but anyone from anywhere else has to come through us. And we have a nice relationship with them. We also in Canada use Applied Nano Tools, and they have a very rapid prototyping system. It's quite quick. It's quite simple. It's only 2 or 3 masks. Uses an E-beam, but it allows you to do some quick tests and cut and goes on prototypes. And we're also working closely with Global Foundries. We had just got involved in aggregating for their 9WG process when they pulled the rug out, and now we have a number of people working on 45, what they call CLO, so 45 nanometer microelectronics with photonics on top. We actually have 8 people in our photonics support group. 7 of them have PhDs in either physics or photonics, and somehow 1 master's degree slipped through our screening process. But all great people, and they're supporting a lot of different initiatives here. So this is where you've talked about building up cell libraries and measured components and so on, and that's the kind of thing that we're doing now to make sure there's a really good toolkit set. And for people who want to actually play with a component, we've built these everything plus the kitchen sink kind of photonics devices that you can put on the bench and measure and try them out. And it gives you a chance to maybe, if you're a startup, do a minimum viable product and demonstrate it, or if you're a student, to learn about how these photonics devices work on the bench. And we announced last year an IBM interface. So some of you have talked about the difficulty and expense of connecting fibers. This will connect 12, 20, 30 fibers at a time. It's a purely mechanical alignment, and the initial results we got were 1 to 1.2 dB level loss in the connector. So very good, no active alignment, very quick to do. So we're working towards making that a standard industrial process as much as possible. And we're proud to be a member of Photons Canada, EPIC, and OSA. And that's it. Thank you very much.
Thank you very much, Gordon. Thank you. And the next speaker is Gloria Heffler.
Okay, thank you. Thanks everyone for attending today. Let's see if I can get this going. Can you see my screen?
Yeah, that looks good.
Okay, great. So my name is Gloria Hoffler. I am a senior director at Infinera, and I've spent, let's just say, over 25 years in the area of photonics. And so I will start with a quick introduction of Infinera, and will likely make similar points to all of my colleagues, which make my job easier today, and then try to highlight the state of the foundries while providing an overview of indium phosphide PIC services to illustrate where we really are today and why some of these gaps and challenges are still there and how we've tried to address it, considering where the industry is today. So Infinera is an optical network solutions company. We're organized as a vertically integrated company with indium phosphide PIC fab in California, packaging and manufacturing plant in Allenton, Pennsylvania. And this allows us to optimize and co-design various aspects of the products to deliver the best performance. And over the years, we have also developed competencies and RF interconnects to meet the demand of higher data rates to keep up with the PICs. So traditionally, all our infrastructure goes to support product lines, which are high performance coherent modulation optical engines that are seen on this line now. But over the past few years, we've made our PIC technology open to users through Foundry services, which obviously is the topic of today. But we wanted to highlight that when we look at these engines, we have all the competencies today in-house that allowed us to see what silicon foundries do, what is the state of packaging, and that's really what has guided the foundry development. So let's start with the highlights of the fabrication line, which is used to produce the foundries PICs. We've seen the similarities and differences between silicon photonics and silicon ICs, and I'll try to highlight some of those as I go through this slide. We use a multiple wafer MOCVD epitaxial process to build up optical stacks that are made of very different components, indium phosphide and indium gallium arsenide thin layers and quantum. So this is very different than the silicon industry. We perform standard growth, etch, and regrowth steps to create specific gain regions and active passive regions that are all integrated into a low loss indium phosphide material. So we then follow that with a standard wafer fab process, which is done to complete the isolation and the metallization interconnects, and then it's followed by pleating and AR coating. Again, this is slightly different than it's done in silicon. So we have edge waveguide facets. We run then functional tests and QA before we ship the modules to shipping. And we rely on rigid statistical process controls to have some sustainable yields. So to develop and provide a robust process for the foundry and for the PIC offerings, we need to really have a deep understanding of our manufacturing capability, and the design rules decks are designed around that. And that is very similar to what happens in silicon photonics and in silicon today, but more so in silicon because the volumes and the understanding and the capabilities of the lines are very well understood. So what we do is that all our processes in the fab are controlled using tight process capability indexes and CPK. So at the end of the line, tests from the product PICs are used to draw correlations with PIC performance and verify that the rule decks are correlated to process capability. We feel this is really an advantage of using a commercial line because it allows us to develop a foundry that typically will have very low volumes from emerging and specialty applications. So currently we have over 90% wafer fab yield and CPK is over 1.33 in all our processes. So this methodology is very similar to what is used in the silicon industry and has really allowed us to transfer learnings from one PIC platform to another. This is basically what we've demonstrated with the use of 1.2 terabit optical engines that it can be then transfer from the C band to the L band. And again, this is very similar to the process that is used in silicon industries. And it can only be done because we have the volume to support the statistics. So we've made the foundry access of multiple functional components spread out over two major PDKs. And I won't go into the details, but We have basic building blocks like in silicon foundries, and we also offer calibrated IP blocks such as IP modulators, filters, and balance PDs. All these functions are available in a verification chip, and this was to address, where testing. David mentioned the testing capability in the industry today. So we have found that many of our customers have found these evaluation chips very handy, because when ramping up their test infrastructure, this helps them overcome the gaps in test standardization and definition. It also allows users to start designing control chips that are tailored for their specific applications. So this is what the foundry flow typically works for us, and this is something that we developed in collaboration with AIM Photonics, which allowed us to address a lot of the barriers in scaling the PIC foundry into a commercial prototype. So because it's very difficult to jump from production ramp directly into conception. So we start out with interactions at the PIC design with specifications, and these conversations happens between PIC designers. So at this point, we don't expect users to have prior PIC or layout experience. We just take the schematic designs and convert them to layout, and the customers then receive a PIC prototype. So then again, this helps to provide them with a standardized prototype that they can focus then on their application. Completely EPDA environment, and so that shortens the cycle times from prototype also to ramp up. And just to illustrate some of the comments that others have made, we've developed working on a environment that has simulations is also very important. So we here demonstrate BPI Photonics. We've also worked with Synopsys to provide a direct path from simulations to schematic generation, and then to layout. Users can also use Cadence, which is a more mainstream way of looking at this symbol libraries similar to the IC industry. And this is just to show you that you can go directly from simulations into a interoperable, the interoperability of the tools is not there. So we've created some coding around that. So it allows users to go between simulation and Cadence virtuoso in this case. And then another part that's really important is the validation. So for being able to provide experimental validation to the simulations, and that is really important because these test vehicles have been created to experimentally validate the tools that are used for simulating the circuits. And in this case, just to show you the capability, I have a VPI coherent circuit that's been validated with a run. I think that's probably over my time. So thank you very much for your attention.
Thank you very much, Gloria, and I would like to thank all the panelists for excellent presentations that give, I think, a very good overview of the current status and outlook for Photonics Foundries. So I would like to open up the floor for discussion. Obviously, if there is anyone that is attending that would like to comment or ask any questions, please say so through the chat line, and then I'll make sure that that gets discussed. And actually, Gordon already sort of submitted two topics for discussion through the chat line, the first of which relates, I think, about the quality of the current design software for photonic components. So Gordon, would appreciate if you would like to expand on that and see what do we think about that.
I should have known I'd get in trouble.
Shoot the messenger.
Yeah, so we have a lot of academic researchers who don't like paying for tools at all, despite the fact that in Canada we have a heavily subsidized program for accessing Tanner and I should say Siemens and Cadence and Mentor and everything else. But they'll use K-layout, for instance. And we've talked to a number of people, not only in the photonics area, but also we just ran our first base camp on superconducting circuits, and they all seem to just standardize on K-layout as their edit tool. And it's wonderfully flexible and allows you to put in Python code and do all sorts of wonderful things, but it generates frequent GDS errors.
Yeah.
So we've had to clean those up on a number of occasions. It's been very unhappy. So we do try to get people to go in and use one of the larger companies' tools. And K-layout works for the moment, but sooner or later they're going to be verification tools and simulation tools and all sorts of things, whatever the photonic equivalent of static timing analysis and parasitic extraction is going to be. And that will all be developed by the larger companies at the cost of billions of dollars a year, right? So we really want students to be trained and the next great bunch of photonics students to be trained in more than layout, but in all of the other stuff that goes along with doing a good design that's going to be first time right.
Yeah.
So that's very good comments. This is Dave Hammer. I might just follow up. I agree with you that there's a lot of people out there really want to use the lower cost platforms for laying out their circuits. And we've supported K-layout throughout all of our platforms and also have invested time and energy on the DRC decks and other aspects of it. But when it comes to more complex heterogeneous integration and simulation, K-layout really has to feed into other tools, right? So it's very effective for support, but it also is dependent on, like you just said, how you described it well, the rest of the infrastructure to really design the entire system and circuits.
Yeah, well, actually, I think this was triggered by one of my comments that we should. And actually, well, it's very fair comments, and I fully agree with what you are saying, especially if you want to go to more mature stuff. But especially in Europe, there's a lot of startups, a lot of SMEs, a few 20 people companies who have brilliant ideas, and they cannot afford these expensive licenses. And I'm not at all. Well, actually, we do not support K-layout as a design tool as such. But what I want to do is to come to a type of standardization on PDK level that you can the way you just describe your PDK. So if you obey the rules, if you obey the DSC rules, you can adopt a PDK, and you have to provide us with building blocks with black boxes that are described in the correct way. We provide a standardized description of what they should look like. If you can generate those with a software suite, even a homegrown software, as long as you use this, if you read in our standard description of the PDK, you can give a valid GDS out. But don't, I 100% agree, you should not just lay out something on the back of an envelope or, well, and making a lot of errors, because that is not the way to go to bring it forward. But I'm more thinking of standardizing the way the PDK is described, so that multiple software companies can adopt it, can read it in the same way. And then, of course, if you want to go to advanced and also the parasitics, especially if you go to the hybrid integration, especially if you want to integrate with electronics, then it's a completely different deal. But to get people started with their first steps in photonics, to get also these innovative small companies introduced to photonics, it makes a lot of sense to have a low threshold access outside the academic community, because I think that is a different. The academics are very well served with CMC and as you point out, but also there's Europractice in Europe that supports them. But it's the SMEs that don't get this type of support, and that's where a lot of the innovation is.
So we went back to all of our vendors of CAD software and we told them, look, academics could never afford your tools, but a lot of SMEs can't either, and they need to get to a financing or a minimum viable product. Could you do something for us? And so they have offered us lower cost licenses, which we serve in our cloud so that we have total control over the license and we can give them business intelligence on how much the license was used and so on. But Siemens mentor, Tanner, were very helpful in that. So we can offer that tool for Photonics.
So I guess we've used a slightly different approach, as I mentioned before, and our approach has been that interoperability is not there today. There are consortiums like AIM that have been trying to work on pushing, and other companies have been trying on pushing this standardized building blocks. I mean, but even in the silicon industry, that's not the case, right? I mean, even we work with various silicon foundries, and they don't have standardized PDKs. So I think that's going to be very difficult to get across the entire industry. So our approach to that was find a common, we use SPICE like net list files to accept schematics, and so then we bring everything into Cadence. We use Cadence. We could have used Synopsys as well, but we use Cadence Virtuoso to do this, and then we do all the caliber, all the DRC, and all of that, and that really lowers the barriers for the users, because at the end of the day, what we really want is to create a larger user pool. We want to get the photonics out into these applications and the end users to have their chips, and there's enough on the test side, on the standardization of the test side, that they also have to deal with, that if those barriers are so high, they're just not going to try the PICs, and they're going to stay in an academic setting. We really need these emergent applications to increase in volume. And so that's why we've taken this approach of do a lot of the coding in-house to pull these netlist files. We can pull them from VPI, we can pull them from Synopsys, we could probably pull them also from Lumerical. I mean, with once you have them in the standard SPICE-like netlist, things become a lot simpler. But again, that's just our approach.
Yeah, can I make a comment about education workforce development? So, we're really trying to bring up a whole generation of photonic designers, right? And people that are knowledgeable. And so you're going to have PIC courses, right? You're going to have photonic integrated circuit courses. And those things almost rely on the EPDA tools in order to sort of do this. So that, it's also from an education point of view, driving some standardization. You can't have courses where there's just a plethora of smaller platforms, right? So you really need a couple of standard ones. And by the way, you mentioned K-layout and some other ones, in order for students to really get in there and have the experience and learn the design tools. That's also sort of driving it from a component design point of view.
Actually, there is a question from Naresh Chand in the audience to the whole panel. The question is, are the integrated circuits cost effective compared to discrete solutions? So anyone who wants to pick that one up.
No, I don't have the specifics, but maybe because I can comment on this because we make integrated circuits for our as our optical engines at Infinera. We don't before we started working on the foundry solutions, all our PICs went internally. So all our optical network systems have PICs. So they have those systems have to compete, right? So when you start looking at the cost of packaging and reliability, integration makes a lot of sense, just like we did for silicon ICs.
Actually, something that some people talked about as well is hybrid integration rather than monolithic integration. So what is the role of discrete, hybrid integration, monolithic integration? Is there a place for all of those? Anyone who wants to pick that one up?
Well, I think there's a role of both. I think for hybrid integration, It really depends on scale. It's I think we can do a lot on indium phosphide, but even a lot more can be done on silicon. So we have to find the best of both, and to find the sweet spot where the two can be integrated. And if you just if you have a very complex passive circuit, then just putting a indium phosphide laser on it is probably the best choice. If you have a sophisticated network of amplifiers and modulators, then well, you have to really work out the where the sweet spot is in the integration. An optical connection is by far more expensive and less tolerance than an electrical connection. I think that's where we have to see if we can reduce the number of optical connections. That will be the cost-effective solution in the end.
Any other comments on this? Which is the best way to go, or the current? What's the evolution? Discrete, hybrid, monolithic?
I think there's long life in silicon photonics because the equipment, as someone said, it just the stuff doesn't scale. It's the wavelength of light, and that's going to be it. And so they'll be fiddling around with process and materials and that kind of thing, but the equipment's going to last a long time. So it's a bit of the beauty of silicon photonics is that you can tool up a fab and expect it to run for 10 years, not 18 months.
Actually, changing topics slightly, David mentioned that in his slides that photonics is critical to the future of high-performance microelectronics. And actually, I personally could not agree more. I think that looking ahead, one big driver potentially for photonic integration is the fact that microelectronic integration will need photonics to be able to go forward. So since David, you brought that up, if you have any further comments on that, but obviously it's open to everyone to comment on that.
Can I show one slide?
Absolutely.
Okay, so let me show this slide. Here, I can try once more if it works, fine. If not, let's see. No, it seems to whatever. Can you see the screen okay?
Yep.
Yeah, we see the roadmap for merging photonics and electronics.
Okay, all right. Oh, now it's letting me actually duplicate. Yeah, so this is actually a figure taken from this article by Margaret. You can see John Bowers in it as perspective on future of silicon photonics and electronics. So this is an article that's actually talking about just the question you asked. And what you see here is for merging photonics and electronics, they started out with optical links, very separate. Then they kind of started putting them on the PC board. Now they're kind of looking at more laminate or more dense things, 2.5D, maybe getting them closer, putting some photonic elements. I think eventually you're going to have co-packaged. Other people call it optics on board. This intimate integration, we're kind of up here, but eventually we really have to get to a place where it's really part of the process. That's one of the things that I was trying to talk about a little bit in some of my slides is this conundrum. A CMOS fab, if you're in silicon photonics and you're trying to take advantage of all of that control of 300 millimeter, you're just not going to walk in there with these different types of materials. It's really, this is a heavy lift to get to this sort of an integration. But you're just not going to get this high I/O and capability and speed and dense circuits without gain elements until you do this. So I think this is a very large driving force, and it's something in the industry that we're going to see more of. Today, everybody is focused on the resiliency of the supply chain and microelectronics fabs being completely booked. But I think that this is going to start emerging, and you're going to see more and more driving to get this intimate integration and take advantage of it. So just a comment.
Thank you, David. And any other comments on this? I think this is a really crucial topic. What could be one of the main drivers for integration, but it needs the electronic side as well. It cannot be just photonics. All right, so in what you were saying, David, obviously packaging becomes very important. So we placed a lot of emphasis on, there's been a lot of discussion on the semiconductor side. How do you see the perspectives for the packaging side evolving, such that it can support this integration.
Yeah, so you were
Yeah.
mentioning EPDA, earlier. I think assembly design kits, there just isn't really standard flows that go all the way from pick sort of all the way through to packaging. Just to even getting a really good assembly design kit side. I know Cadence has their heterogeneous integration tools and integration. Synopsys is looking at assembly design kits, but the infrastructure is just not there, right? I think that's a great place. And I think EPDA is the place that can help drive standardization and trying to get to more off-the-shelf sort of processes with models that people can utilize to bring costs down. I think that's a big aspect. I mean, I look at some of the packages like Gloria was showing some of her packages. They're really impressive, right? And I'm just, how do we actually get an EPDA platform and a whole packaging infrastructure around standards to make that complexity available and inexpensive, especially from different applications?
Gordon, are you addressing packaging aspects of CMC at all?
Well, I'm really on the hot seat today. So we work with a couple of Canadian suppliers. We work with Tyndall, obviously, and the thing for us has been we have academic things that come out. They have not been designed for packaging, obviously, and so we get quotations anywhere from 3,000 euros to $15,000 Canadian to package 3 devices. So it's very painful for sure. But on the academic side, they're not going to go into volume, so that's a big issue. And we also offer a silicon interposer technology that can be used to co-package stuff, which we hope will come up with a sort of BGA connection to the board, and it'll be much easier to co-package devices on that. It comes with a design kit and all that sort of stuff. So yes, we're trying to tackle it, but painfully.
Sorry, Gloria, go ahead.
Sorry.
Go ahead, sorry.
Packaging is highly customized to the application, right? So I mean, in the telecom and datacom industry, it's the SMA, the standardization of the packaging requirements has driven that, but it's a volume, right? So for some of the emergent applications, it's very difficult to standardize packaging. I mean, if you want a package for a LiDAR application is going to be very different than a package for another type of sensor that only requires a laser on the detector for like a medical sensor, right? Even though it's still a sensing technology. So I think it's very difficult to standardize packaging. I mean, Infinera has been doing co-package for a long time and very densely co-packaged that I've shown, but that's for a very specific application. I think when you start looking at a multitude of areas that we want to open up, it's very difficult to do that. And so, as a foundry, I think you need to address it, either by saying, okay, you're going to build this prototype. This isn't your final thing, but once you have a final widget that what size and power you're going to require, then you have to design the package specific for that application.
So for the short runs, we have a control project called Protopack where we're trying to create 3D libraries so that you can create a package and just drag in an SMA connector or drag in a fiber optic hole pass through and that kind of thing, and see if people can cut and paste, sort of a PDK with the reference library for packaging, but it'll be the onesies twosies, right?
Right. I mean, we provide standard interfaces, standard electrical interfaces, standard optical interfaces, and then the users can design around it or provide, evaluation chips. But these are all sort of, Band-Aid solutions to the problem. But I guess it's because we see the problem as a volume, right? So it's, that's just to get users to which application is going to create the large volume. So, how can we help these users, by creating the standard interfaces, by providing a standard probe card, providing a standard, IO, how do we make life easier for them so they can figure out, if they're going to use this PIC, on a LiDAR or on a free space optics or on a medical application, or a clock something like that.
I think
Sorry, go ahead. Go ahead. Sorry, I'm sorry, Luke. Go ahead.
And so the standardization on packaging, as you all say, it really makes a lot of sense to standardize interfaces to have but to really standardize a package that works very well for prototyping indeed, but not for volume application. If you look to our customers, the one that have a real product, they do the packaging themselves, or they have developed a customized package, because that in the end, if you scale it in volume, that is the most cost-effective solution to customize it to your needs. And for I think there's some improvements to be done on the prototyping area, that we have a more standardized package that can help people, because they don't know how to deal with a chip. If they have a fiber connected to it in a standardized way, or some RF connections to it, that will help. But that is only well, to do the first few chips, and after that in volume they have to customize it to their needs. So I fully agree to what Gloria is stating here.
Thomas, how do you see the packaging situation from a Ligentech perspective?
Yeah, I mean, I do agree for the volume, you want to have it customized, but also see, I mean, you also have our standardized package. We had to develop it, and packaging cost is extremely expensive. It's slow, it takes long. So I see it as a big burden for the customer. And I like a statement a customer of ours said recently: PICs are useless until they're packaged.
That's very true.
Or fiber connected. And that's what you should not forget if you talk about all these nice wafer technologies, that for a lot of the customers, they're useless as we ship them. And we have to bridge that gap. And that's key. And even in R&D, and that's not yet solved to my knowledge. I mean, there are solutions out, but they are not as easy to go smooth as they should be to move forward fast for our customers.
Yeah, that's very true. So we have about 3 minutes left in our panel discussion. We've covered a lot of topics. I don't know if there is anything else that we haven't covered that anyone would like to bring up. You have 2 minutes if you have anything in your mind, or for the audience to make another question.
I don't know if anyone else has run into this, but I believe that any device that has an integrated laser is controlled goods under the U.S. export rules.
Oh, yes.
A photodiode, a laser, right, and a waveguide. All it takes.
Yeah, that's a headache.
Yeah, that is a very good point. And that's obviously something to think about.
I don't know how that works in Europe, but I assume that they have similar, ITAR type of regulations and export controls. So,
Well, there's export control on various aspects. Indeed, while it's lasers, it's a certain power is required, but yeah, there's rules and regulations for that.
sub-assemblies, building sub-assemblies helps mitigate some of those issues.
Oh.
Actually, there's another question. We have 1 minute from Naresh Chand. How are foundries doing financially? So anyone? I guess they're all doing very well.
Business is hot right now. It's hot.
I guess the photonics industry is doing well, which is
absolutely
good thing, and very easy to see why. So I would like to thank all panelists. This has been a really fruitful and nice discussion. I really appreciate all the comments, and the conference is just starting. Today is the first day. So unfortunately, it's still virtual. Hopefully we will meet sometime in the near future, actually face to face, and I'm looking forward to that. So thank you very much, and looking forward to seeing you all soon.
Yeah, thank you, Daniel, for all the organization. Everyone else, thank you.
It's been a pleasure.
Thank you all. Thanks.
Bye.
Bye-bye.